Hello. Today we'll be talking about partially ordered sets and Hasa diagrams. So we'll go ahead and get started. What's a partially ordered set? Well, this has the properties of being reflexive, antisymmetric, and transitive. And so if you had, say, a relation that didn't fulfill these properties, maybe you say, okay, A relates to B if maybe A multiplied by B is non-negative. Well, this relation is not doesn't fulfill antisymmetric, so it would not be a partially ordered set. So I could say maybe, well, 1 relates to 2, and I have 2 relates to 1, but these elements are not equal, and so like we can say it's not antisymmetric. So this wouldn't work for us. We could consider though, and often for Hasse diagrams, you consider like the divide relation. So what if we said, okay, A relates to B, and maybe, yeah. If we could say A divides B, or we could say alternatively, like, if B divides A, that would give us different relations. So say if we had a set that's similar to the one we had in discussion. So maybe we say, okay, our set is like 2, 4, 6, 9, 12, 18, 27, 36, 48, 60, and 72. And we're relating these things under, we'll say, they'll do this first definition of A divides B. Then we'd say, okay, I know that if I were to kind of draw these out, I could like kind of draw arrows and say like, okay, 2 relates to itself, 4 relates to itself. I know 2 relates to 4. Maybe I'd do some arrows to say, okay, 2 divides 4, and 2 also divides 6, 6 divides itself. I can kind of draw these things, but because I know that for all of these, I know I have transitivity. I know I have like they're all reflexive, and I know that I can't have something where I cannot have this kind of thing where there's 2 different A and B that relate to each other. So then I can kind of simplify this with a Hasa diagram, and I'll basically say, okay, if 2 relates to something else, then I say, okay, I draw like a line up here. So maybe 2 relates to 4 because 2 divides 4. In other words, like 4 divided by 2 is equal to 0 is what we mean by like divides. I could say, okay, 2 divides 6 as well. I know that 6 and 4 both divide 12. And so I won't do a separate like arrow from 2 to 12, even though like that kind of exists implicitly with this relation. So I'll just kind of leave that like kind of as implicit and not actually write that in with the Hasa diagram. And then if I'm also, okay, so I have, yeah, we have 2, 4, 6, 12, 9. We don't have that related to anything quite yet. But if I have 18, I could say, well, that's like related to by 9, and also by 6. And I could take 27. Well, 9 relates to that. None of the others do so far. And then 36. Oh, well, I can get to that from 18 and from 12. And then 48. Well, I'll just be getting to from 12 here. Although like I also get to it from like 4 and 6, of course, but those are kind of captured already. And then 60 we'll get to like 12 divides 60. And for 72, well, 12 divides that, 18 divides that, as it's 36. So yeah, so this is not a super well drawn, but this is a Hasse diagram that can kind of show us like everything in the relation with like, without having kind of all these extra arrows and things. And so then we can ask some questions about what is like maximum or maximal. So here we'd say, okay, maximal means that okay, nothing is kind of like nothing is kind of above this in the Hasa diagram, or there's nothing where I have this like, say if I talk about A as a maximal, I don't have this kind of thing where A is the first element of a relation. So I could say, okay, 60, nothing, even though, yeah, 60 is like less than 72, I don't really care about this here. And so I could have, yeah, 60, 72, 48, and 27 being kind of my maximal elements. A maximum is saying like there's only one of the alls, and this is true for like minimal as well. And so I don't have a maximal. I don't actually have a minimal either, but if I wanted to, I could say maybe I add in one, and well, one divides everything, so then I can say one is my like minimum element as well as like the minimal. And then we can have other properties like an upper bounds and least upper bounds that we can kind of use the Hasa diagram to analyze. I will also say we can. So let's consider now like what if we changed it to be, instead of A divides B, what if we did B divides A instead? How would that change our Hasa diagram? So basically, that would basically flip it over. If we said instead we'll do B divides A, then we say actually here, well, 2 or 4 is like divisible by 2, and so like 4 relates to 2, and 6 divisible by 2, and so 6 relates to 2. And I kind of would draw this like this whole thing in reverse if I switch it around. And so then I can still like say in this case, if I draw like the whole thing, maybe I say actually if I just said I made this set with just these 4 elements, I'd say actually here like 12 is my like minimum element, because yeah, like 12 like is divisible by 6, 12 is divisible by 4, and also 2, so everything like is divisible by 12, and 2 would be like the maximum, so like 2 is the thing that divides like everything. And so I can kind of change like around the order of the relation. If I said this is like divides versus like is divisible by, or I guess if we say A is divisible by B, or we say like B divides A. And so kind of how we do the ordering can really change how the Hasa diagram looks. But yeah, but I guess it's kind of this idea of like a partially ordered set. I will say also, yeah, so for total ordering, the idea here is that we can like kind of we have to obey the rules of the partial order, but we can make kind of any total ordering we want that follows those rules. So I could say 12 is less than 6 is less than 2, or is less than 4 is less than 2, because I know that I have to have like 12 less than 2. I have to have like 12 less than 6, 12 less than 4. If I added this other element into 7, it doesn't relate to anything. I could have 7 at the beginning. I could have 7 at the end of my total order. I could also switch up the order of 4 and 6, so they really like I can't compare them, and so they look the same to me in terms of how they're ordered. So I could say maybe I have 12 is less than 4 is less than 6 is less than 7 is less than 2. And so I guess as long as you obey the rules of the partial ordering, I could say I couldn't have something where I say 2 is less than 12. I couldn't do that because that would disobey this Hasa diagram here with like 2 and 12 there. But as long as I follow the rules, I have a valid total ordering. So with that, have fun with some Hasa diagrams.